Welcome to a lesson with Dr. Powell. We're going to take a look at two different kinds of exponents. So first, we have exponents that we're used to, like 2 cubed is equal to 2 times 2 times 2. Now with functions, you can also use such an exponent to represent the multiplication of the output. Perhaps, like for instance, if we have like f of x is equal to x plus 1, we could say that f to the third of x is simply, what do? It's the function that's represented by multiplying the output of the function to itself 3 times. Okay, so that's called a multiplication exponent. Now, we have other kinds of exponents that are often seen in algebra, but the notation that we use is the exact same. That creates confusion. For instance, the inverse cosine function. A lot of people might think that this means a multiplication exponent. Well, that means we're undoing multiplication, so we're dividing, right? So but this unfortunately is not equal to 1 over cosine of x. That's because we're thinking of this exponent in the wrong way. This exponent really should be circled. So to distinguish that it means something else. What is an exponent in relation to? Exponents mean like repeatedness of an operation. In this particular case, this is a repeatedness of multiplication. Repeating multiplication here. This is repetition of something else. Okay, so this is something else. This is not multiplication operation, it is composition operation. So we'll come back to this example in a minute, but just to be clear though, this is not really, cosine does not have an inverse function where you're swapping your x's and y's and thinking of a function that undoes the action of another one. It doesn't really have it because it's not one-to-one. I mean, its graph is very wavy and it doesn't have an inverse. So this is also notation which is deceiving. Cosine doesn't have an inverse, but a restricted version of cosine does, particularly if you restrict it to an interval where swapping x's and y's, wouldn't do this. So you get something that's not a function. But you restrict it nicely, and then you can have an inverse. All right, but we'll talk about that again in a minute. All right. So, So wait a minute. Let's kind of understand what that means, though. These circled exponents. What do you mean? It's repetition of what? Of composition. What is composition? So if I have a function, say like this one right here, f of x is equal to x plus 1, and I have something like f of x. So I do an action on x. What does the action of x do? Well, it takes x and it does something with it. It outputs x plus 1. So you act on x to make x plus 1. And then you act on x plus 1. And the action is you put x plus 1 into here and you get out, and what do you get out? You replace x with a slot and you put in what we're plugging in, x plus 1. Good, we're going to get x plus 2. Okay, so this is equal to x plus 2. This is repeated action of f. A repeated action of f, and we can notate that by f of f. So it kind of mimics what we're doing here when we have like f times f. Notice the closed circle. Notice the open circle. It's an operation here. We can say f times f times f. Here this is f of f, and instead of saying times, we say of, because it's a different operation. It's a composition operation. It means we act by f, then we act by f again. Notice that we do it in this order, from right to left. Just like when we read function notation, input to output, like plug x into the function f, thinking that way. Well, same thing for this action. So do f, then do f again. And if we wanted to do f, then f, then f again. In fact, we can just use this notation. We don't even have to put a of x, just to represent the function of doing these actions so many times. So do f, then do f, then do f again. So this is another function, and this is, we could use this circled exponent right here, f circled exponent 3, to represent this function action. All right, so this one would be f to the circle 2 power. All right, now we have another function which is nice to work with. It's the identity function. 2 letters, but I'm thinking that it's going to be thinking of it as 1 letter. It's just a name, right? Just like cosine's a name or something like that. So identity function of x. I'm going to call it the identity function. Identity function of x is simply x. What? It's a nothing. It's the do nothing function. Now, is there a do nothing multiplication number? So you multiply by it, does nothing? Well, yeah, 1, right? Multiply by 1, it does nothing. So 1 is the multiplication identity or multiplicative identity number. But here, the identity function is the do nothing composition, do nothing function with respect to composition, not multiplication. So, for instance, if we do f of identity, what is that equal to? That's simply equal to the function f, right? Let's just think about it. F of the identity of x, what has happened? X goes in identity, nothing happens to it. Yeah, you just get f of x. Should be pretty clear, right? So it's the do nothing thing. And notice that if we have f negative 1 exponent composed with f itself, and we can put a little 1 here, meaning it's just itself. It's just what it is, just like in multiplication, 2 to the 1 is just what it is. So what happens here? Well, this action undoes that action. Let's think of, well, let's remind ourselves what this even means. What is f to the negative 1 in this case with a circled exponent? It means inverse function. So we're thinking of an inverse function. What does inverse function mean? It means it undoes the action of f. So it does the reverse action, like x's and y's are swapped or something like that. So if we have, for instance, f of x equal to x plus 1, so you're adding 1 to something, what's the inverse action? Subtract 1 from something, right? F inverse of x, but let's use the circle exponent, should be equal to x minus 1. So in that particular case, let's see, if we add exponents, add these circle exponents together, we should get f of to the 0 circled power. Now, what is to the 0 power with respect to an operation, like respect to composition? It's always the identity with respect to that operation. This should be equal to the identity function. Well, that should be clear. I mean, like, you know, if you have 2 to negative 1 times 2, where this is a to the 1, these are multiplication exponents. This means you undo the multiplication action by 2. That's the same thing as dividing by 2. So that just means dividing by 2 or multiplying by a half. That's all that means. It's undoing the operation. 1/2 times 2, and you end up getting 1, which is the multiplicative identity with respect to multiplication. Here, this is the composition identity with respect to composition. These exponents add, you get 0. Great. So again, we could do something like this, like f2 of f negative 1 like that. Of x, what should this be? Add the exponents, you should get f1 of x, which is just simply f of x. You could even have things like this, f negative 2. What is that? Well, that's going to be simply f negative 1 of f negative 1. And we can actually compute that. So f negative 1 is x minus 1. We can check this out. So we're going to plug in the output of x of f inverse, which is x minus 1. Then plug that into, and we're plugging that into this. So we're replacing this x with x minus 1 to get x minus 1 minus 1, because this guy right here is being plugged into there, so x minus 1 is being plugged into this, right? So x minus 1 is being plugged in per place of x, so we end up getting this, and notice we end up getting x minus 2. We just computed f raised to a composition exponent. It's just repeated action of a function with a composition operation. And really, okay, so whenever we have inverse functions, we should always use, at least in our minds, think of circled exponents to kind of keep them distinct. So cosine to -1 circled exponent. You could also do sine to -1 circled exponent, but just remember, this is sine restricted inverse function. And that actually becomes important sometimes because it doesn't really cancel out things as well. It won't cancel the cosine function necessarily completely out. So for instance, or the cosine function won't cancel with it. So depending on what side we place it on. So let's see. So the cosine function itself is restricted from 0 to pi, okay? And cosine inverse undoes that, which means, so the domain for the function we're taking inverse of is actually this. Okay, so maybe just, there's so many things to be confused on. I'll just circle this whole thing. All right, we're taking the inverse function of cosine restricted, right? That's the domain of the function we're taking the inverse of. So it actually is also the range of this inverse function. So 0 to pi is actually the range of that inverse function. It can only output things from 0 to pi. In particular, if we did like, so if we did cosine, so if we do like cosine of cosine inverse, so cosine of cosine inverse of a half, what should we end up getting? Well, 1/2 is sent to an angle between 0 and pi, and that angle is plugged into cosine, and it undoes it nicely. And the reason why it undoes it nicely is because we're actually what we output is actually something in from 0 to pi, so it's as if we're plugging it into cosine restricted. So this actually does undo itself very nicely to give you a half. But if we reverse the process and you think about cosine inverse of cosine, right? And let's think of that as being a circled exponent, all right? But remember, there's really a restriction here. It's not really truly cosine, okay? Because if I plugged in like cosine of negative pi halves, I'm not going to get negative pi halves out because the range with output by cosine inverse is actually restricted to 0 to pi. So it can't output negative pi halves. So this actually is not equal to the, it's not going to be equal to negative pi halves. And in particular, this composed with cosine is not the identity function. So there was some issues there. So, I mean, you have to be a little bit careful with these circled exponents. They don't always cancel out because only, like in this particular case, because we also have other problems with our notation. This is not cosine when they cancel, right? Where we can't take the inverse of cosine. We have to take the inverse of cosine restricted to 0 to pi. Just a little thought on that. But other than that, I hope that this little description has helped you to think about the different types of exponents that occur. Maybe just one more thought before closing. This is also something that comes up a lot, cosine squared of x. A lot of people get confused on that. I mean, like, what's it? Well, this is simply the function cosine of x, and then you're taking the quantity squared. So this is actually a multiplication exponent. and all you're doing is you're just finding cosine of x and then you're squaring the output. A lot of different notations that can come up. Thanks for watching.